they're generating.
Sorry to jump in.
Yeah.
The history graph.
Okay. Yeah.
So does this mean that instead of taking a dot product with every word, vectors for every word, you're only taking a dot product with these set of words?
Yes, basically. Yep. It's not necessarily the dot product. It could be any variety of attention, but yeah. Yes. Yeah.
What about rare words? The ones which occur very few times.
So that's a good question. Handling rare words is a problem in these models in general. The most common way to fix that nowadays is to basically take your corpus and split rare words into multiple words. So an example of that would be, oh, thanks, would be decide. Let's say for whatever reason decided wasn't very common. What you do is you split this into decide and then D. So let's say decide is more frequent. And then what this does is this makes your sequences longer, but it removes unknown words or very rare words. This is called byte pair encoding or subword units or stuff like that in the literature, and this is very useful. In this case, I don't know how it interacts with this. They're doing language modeling here, so if you do language modeling, it makes things easier because you don't have to actually generate things, you just need to score them. But I imagine that something like this would also be useful in this case as well. Sorry, to answer the question more directly, this helps ensure that you have no low frequency words. All your subword units are high frequency, and then you just need to combine them together in the appropriate way. So one problem with this, though, is we talked before about like training the model to optimize or training the model based on the input, the correct input. There was a question about that at the very beginning. So the problem with these models is if you're training the model on the correct input, basically it seems like a very good idea to often be copying from the stuff that you've already generated, right? Because you get Fed Chair Janet Yellen, and Janet Yellen is going to be, it's always going to be correct. So next time you see Yellen, of course you're going to want to use Yellen. Because it's a rare word that you've seen before. You should increase its probability. But the problem is when you actually take out your phone and write your email using speech recognition like I do, it's not going to get Yellen. It's going to get like yell on or yellow or something like that. And in those cases, then, unless you have some mechanism to correct the previous mistakes, it's just going to continue to do the same mistake over and over and over again. So in the case of writing my email on my cell phone, if I get a mistake, I go back and correct it with text. And because I correct it with text, they can then use that. They can then use that in my next speech recognition results, which Google is apparently doing. It's very good at doing that. But if we don't have a correction mechanism, it will just reinforce our errors that we had at the beginning. There's also methods where basically, in addition to attending to the encoder, you attend to the previous outputs of the decoder as well. So this is kind of like it looks a little bit like a recurrent neural network in that it's conditioning on the previous things that you've generated. Any questions about this? OK. You can also attend to lots of different modalities. So actually, attention kind of first came into prominence through image captioning or basically through image captioning. And in image captioning, you're attending to different parts of the image as you're generating different words in the output. So when you attend to, when you want to generate bird, you kind of attend to the place that has the bird in the image. When you want to generate water, you're attending to the places in the image that have water. This is also true for speech, which you probably heard about. Have you talked at all about like specialized encoders for speech or anything like this, like pyramidal RNNs? Or, yeah. Okay. Oh, that showed up in the last homework. Okay, so you don't need me to talk about that. So also hierarchical structures. So hierarchical structures, you can come up with any amount of hierarchical structures because language is very hierarchical. One example of this would be when you want to classify a document. A document is made of multiple sentences, so you can go and encode each of the sentences independently using a regular attentional model. So this gives you a representation of the sentence itself. Then you have another set of attention over all of the sentences in the document. So you basically decide representation for the sentence based on what words in the sentence are important. Then you decide a representation for the document based on what documents are important. And this has proven useful. Other examples of this include representations of a sentence where you first get a representation of the word based on its characters or morphemes, and then you combine the representations of the words into a representation of the sentence. So this is pretty general. You can use it in a lot of different places. Other things you can attend to are multiple sources of information. So one very nice example of this is translating from multiple languages into a single language. So this particular example has two sources. One is in German, one is in French. And by using both German and French inputs when you generate the target sentence, you are able to greatly improve the accuracy because maybe the structure, German and English is not a great example, but maybe the structure of German is closer and the words in French are closer. Although that's not true, but you could come up with an idea where you have two different like features of a language or two different languages with various features that are similar and useful. Yeah, in this paper here compares multiple strategies to attending to two things. More interestingly, maybe, is that you can attend to two different types of things when you're generating. An example of this is multimodal machine translation. So multimodal machine translation is something where you are given a sentence in, say, German, and then you want to generate, or sorry, what is this? You're given a sentence in English that you want to translate into German, but you're also additionally given an image where the description, this sentence is kind of a description of the image, or it's grounded in the image. So if you think about something like C-3PO from Star Wars or something like that. C-3PO is a robot who is supposed to translate, but he's also grounded in his environment around him. He can see things, etc. So you could think that you could take in the video from the robot, also what was said, and then use this to translate. And there are some nice results for this on speech recognition also, where you look at the face of the person speaking, you also listen to them, and you kind of read their lips and listen to their voice at the same time to do speech recognition. So, yeah, are there any questions about this? No? Okay. Another thing that's become very popular lately due to some very impressive results is something called IntraAttention or self-attention. So the idea is that each element in the sentence attends to the other elements in the sentence. So we basically here we have the sentence and the sentence. These are the same thing, or the same sentence. But for each word in this sentence here, like for this word this, we have this attend to all of the other words in the sentence. And this and this will probably attend to each other the most. But maybe we also have a little bit of is. So then we can generate a vector based on the weighted sum of all the vectors in the sentence. Here for is, an example of the reason why you would want to do this is because is might be a very, like verbs like is, also do, are, sorry, is, do, have. Verbs like this are very difficult to translate into other languages because you have a whole lot of context, and based on the context, they might change. So, or the translation might change. So in this case, when you want to calculate the representation of is, of course you'll want some is, but you'll also want the two other things that the subject and the object of is, which would help you kind of disambiguate what sense you would need in the target language. Then, other stuff like this. So just to summarize, this is your query vector. This is your key and value vectors. And then based on this, you calculate the representation of this. So you can also think of this as kind of a replacement for RNN-based encoders. So normally, for an RNN-based decoder, like your pyramidal RNN or whatever, you run an RNN in both directions, and you take the outputs of the RNN. This, on the other hand, doesn't have any RNNs whatsoever. You're just basically using attention to encode everything. And the good thing about this is RNNs are actually slow. They, especially on GPUs, they have these sequential dependencies between the various things that you're calculating. This, on the other hand, you can calculate this with one big matrix multiply. So this is a much faster alternative to something like an RNN-based encoder.
Question.
Yeah.
If you do the self-attention thing, you would have to have like a word vectors as well to start with, right?
Yes.
Okay. So like if the word is not in the vocabulary, do we just like make it an unknown token?
If the word's not in the vocabulary, yes, you make it an unknown token. Or if you're using something like this, you have no unknown tokens. So this is by far the preferred way in machine translation nowadays, because dealing with unknowns is a huge pain. So by just splitting things up, if you don't have any unknowns, you don't have to deal with that. Yeah. Anything else? Okay. So just a brief mention of how we evaluate things, because this becomes very important in sequence-to-sequence or attention-based encoder-decoder models. And the basic paradigm is we have a parallel test set. We use this system to generate translations or captions or whatever. And then we compare the translations with a correct reference. Probably the best way to do this is to ask a human to do the evaluation. So if you have a bunch of different outputs, let's say the first one is correct, we would have the person evaluate it. There's a bunch of different ways to do this. One is adequacy. Adequacy is basically how correct is the sentence, how much information does it convey correctly. Fluency is how fluent is the sentence. So in this case, this sentence and this sentence are both completely natural English, but this one is just wrong. So this one is not adequate, but it is fluent. And another thing you can do is ranking or pairwise evaluation. This is kind of the final goal, but it's slow and expensive and sometimes inconsistent. So instead of this, it's very common to use things that work by basically comparing the system output with a reference and saying how close are they in string space. And blue score is one example of this. Basically, blue score is calculating the n-gram overlap between the sentences with some other things like that. The pros are that this is easy to use. It's also good for measuring system improvement. So if you have two very similar systems, then blue is a pretty good measure of whether they're improving or not. The cons is that this often doesn't match up with human evaluation. And it's also bad for comparing very different systems. So if you compare like a neural system and a non-neural system, blue will not correlate very well with how good people think they are. There's also a bunch of other things. Meteor is one example. It's like blue in the overall principle, but with many other tricks, like considering paraphrases, reordering, and function content word differences. This is kind of widely used in image captioning nowadays, I think. It's maybe one of the two major measures, or the major measure. It's usually quite a bit better than blue, and it has the additional advantage of being made here at CMU. So you can show your CMU pride by using Meteor. Another thing is you can also measure using Perplexity. So Perplexity is basically are people familiar with this? Did you copy this, cover this already, or no? No? Okay. So Perplexity, you have a held out test set, and you calculate the log probability of the output given the input on the held out test set. And then Perplexity is basically just taking the exponent and of the negative log probability. This very roughly corresponds to how many times you would have to guess before you eventually got the answer right. So if your Perplexity is 16, you would roughly have to guess 16 times before you got the answer correct. So one of the problems with blue is that it very heavily penalizes anything that doesn't exactly match the reference. So it's very sensitive to superficial differences between the system and the reference. So Perplexity kind of solves this because you are actually calculating the probability of the output. And you're not just giving probability to one single output sentence. You're giving probability to many different sentences and seeing how high the probability of the actual actual reference sentence is. But the problem is this doesn't consider decoding or actually generating output. So I do suggest that you consider evaluating your models with Perplexity. One reason why is because it helps you kind of break apart the modeling problem and the generation problem. So if you have a problem in your modeling, you'll get a very bad Perplexity, and you don't even need to look at your generation code. You don't even need to look whether you made a bug in beam search or something like this. You just know that your model is not as good because its Perplexity is very bad. On the other hand, if your Perplexity is good, you might still have a bug in your beam search and be randomly generating wrong things. And you'll never be able to catch that by just modeling perplexities. So that's kind of one good way to divide between the two measures for sequence generation problems. Are there any questions about this part in particular? OK. If not, I'm happy to take additional questions. I actually, one thing I thought I had added to the slides, but I haven't added to the slides, is there was a very nice paper called Attention is All You Need that some people might be familiar with. And basically the idea, if you haven't read the paper, I'd suggest taking a look at it. But the idea is we take, instead of using the recurrent neural networks for entirely rely on this self-attention here to do generation. And it gets very good results. It's fast, et cetera. It also has lots and lots of tricks, and it's very hard to make work properly. So if you're not an expert, I would recommend either using their code or not using that and just using a recurrent neural network one, which is much easier to make work. Yeah, are there any overall questions? We have about 10 minutes, so I can either answer questions or we can finish a little bit early. Yeah.
So like for some of the translations, you have kind of transliterations of the original language.
Uh-huh.
So would that mean like the individual transliterations of like each symbol is going to be in the vocabulary, or how does that go?
So how do you handle the transliteration in translation? And I guess the short answer is there are ways you can do that, specifically tailored to that, which is, for example, word and character hybrid models. So you generate on words until you get to an unknown word, and then you generate based on characters. But the even shorter answer is now that we do this, we don't really care about transliteration anymore, because transliteration, things will be broken up into subwords, and then you'll generate subwords, and it just kind of works most of the time. So yeah.
We have subwords for like each of the symbols, basically.
Well, so an example would be if you have a name like Fredrickson. This would be split into Fred, or maybe, I don't know, Erickson. And then it would generate the appropriate output in the target language for all three of these, and then you would stick them back together, and you would have a transliteration. So it wouldn't be each particular character; it would be, chunks of characters. If you're interested in doing this, by the way, there's a very nice library called Sentence Piece that will break things into subword units for you and stuff like this, which I recommend. Yeah.
So when you say subword units, not necessarily meaning like the root word and anything like that. It's literally.
This is completely unsupervised. So you have no linguistic knowledge. All you have is the basically frequency counts, and what it's attempting to do is it's attempting to merge together things that have high frequency and break apart things that have low frequency. Yeah. Anything else? Okay. If not, I'll finish early, and I'm happy to take. We still have some time, so I'm happy to take individual questions or whatever. So, thanks a lot.